Okay, so let's talk about continuity. So continuity, you already know what that word means. It really just means that the graph can be drawn without lifting your pen, right? So if you were to look at just a graph like this one, let's say it starts at A and it goes to B. This graph is what we call continuous. Why is it continuous? Because you never had to lift your pen to draw it, right? You're going to go all the way from A to B without even lifting your pen, right, off the paper. Here's another graph that's continuous. I don't know. I don't know if that's straight or not. If you're wondering if that's a straight line. It doesn't matter. That's not the point. My point here is that you can go from A to B without lifting your pencil. There can be little kinks along the way. There's a nice sharp turn right there. We call this a corner. It doesn't matter. The point is it's continuous. Does everyone see that? So what makes it continuous? Well, it's continuous because when I was drawing, let's say we talk about a point C somewhere in between A and B. And yes, in calculus we always put C between A and B. It's not quite alphabetical, but it seems like that's what all the books do. Let's say you want to talk about this point right here. The graph is continuous here because as you're trying to come towards this point, so let's say you go left to right, you're traveling towards this point, towards this point, towards this point, and your y value is getting closer and closer to, let's say, 5, right? When you actually get to the point, you find yourself at exactly 5, and as you leave that point, you find yourself leaving from exactly 5. This is why you don't have to lift your pen, right? You're coming towards 5, you're at 5, you're leaving 5, it's all one smooth way through, right? Let's look at this other graph. So let's say that this is y equals 5, and you're tracing with your pen, right? Here you come, you're getting to the sharp kink, right? You're coming towards 5 in the y direction, aren't you? And then you hit this point, C5, right? And you don't have to lift your pen because you are leaving 5 also. You're going to 5, you're at 5, you're leaving 5. Continuity. So how do you write this mathematically? Well, you'd write it like this. To describe the fact that you're coming in towards 5, you would write this. The limit as x approaches C from the left is 5, right? And when you actually get to C, it's 5. That's written f of C equals 5. That's how you write that in math. The point, the y-coordinate at C is 5. And then when you leave C, you're starting at 5 on your way out. So the limit on the right is 5. When all three of these are in agreement, we have continuity. Okay? And this right here applies to both of my pictures above. Okay, so this conclusion is the same for my first diagram and my second diagram. They both have these qualities. If you're coming in towards C from either side, it's 5 as a destination. When you get to C, it's 5 as a location. That's continuity. All right? Okay, so let's write down the formal definition of continuity. Here it is. Now that we've kind of seen a rough idea. A function is continuous at an interior point if the limit on the left is equal to the limit on the right, and those both are in turn equal to f of C. When all three of these are in agreement, we have continuity. If the AP test asks you to show that such and such is continuous at 4, you have to show all three of these things. So this is what we call a 3-part continuity test. You test the limit on the left. You test the limit on the right. You test f of c. If they all come out to 555, you're golden, it's continuous. If one comes out to 5, the other comes out to 4, sorry, not continuous. Something's wrong. Okay? All right. Another thing that you notice about this graph that I have, both these graphs, is that I started the graph at a closed point, and I ended it at a closed point. You'll see graphs where the first point is open and the last point is open. You'll see graphs that are half open. The first one's open and the last one's closed. You've seen those before, right? Where the endpoints are not necessarily closed. So what do we do with that? Well, please understand that this rule that I just gave you is for an interior point. It's not about endpoints, okay? So an interior point C, and C is something between A and B. Okay? So I was talking here in this rule about points between the endpoints. So this rule does not apply to endpoints. Okay, so this brings up a question. Can a graph be called continuous at an endpoint? What do you think? Can a graph be continuous at A or B? It's kind of a tough question, actually. Let's go back and look at our picture, right? In your picture, would you say that the graph is continuous at B? Not in the same way, right? It's not like you're going to draw through this point, right, without lifting your pen. You're not even planning to draw through that point. You're starting. Same thing with the right endpoint. You're not going to be drawing through that point. So you don't have a left limit and a right limit. This one only has a right limit, and this one only has a left limit. There is no right side. It's not in the domain. However, we need to define continuity for endpoints also. So what are we going to do? We have a slightly different rule for continuity at an endpoint. Okay, so the answer is yes. And the rule is this. A graph or a function is continuous at an endpoint if, and the rules change a little, since there's not really two sides to an endpoint, we'll just make the rule that the limit, let's do the left endpoint first, so that'd be point A, okay? Left endpoint A. It will be continuous, here's the rule, if the limit as x approaches A from the right matches f of A. It would be unfair to require the left limit of the starting point to match the right limit. That is not fair. There is no left side. Okay, so here's a picture of what I'm talking about. If this point exists, and the graph is leaving that point, then we say that the function is continuous at A. Okay, so yes or no, f is continuous at A. Look at the picture. It is. Let's say that this is 5. F of A is 5, and the limit on the right is 5. So it's continuous. Yes or no? The graph is continuous at A. Yes or no? No, why not? Which condition is broken? Like, why is it not continuous at A? F of A is 5, but the limit on the right is not 5, because the branch is coming into some other point. Yes or no, the graph is continuous at A? No, why not? There is no f of A. Right. Okay. So that's how the endpoint works, the left endpoint. What do you suppose the rule is for the right endpoint? So a function is continuous at its right endpoint B if, what would the rule be for this point, you think? Here's A, here's B. What kinds of strict rules do you think we should have for the right endpoint to be considered continuous? Yeah, there's no right side, so you can't talk about the limit on the right. But you could say that the limit as you come in from the left has to match f of b, something like that, right? That's the rule. Good. So you would say the limit as x approaches b from the left is equal to f of b. So this one's a yes. If your graph looks like this, it's a no. Not continuous at b. Why? Because the limit on the left is higher up than f of b is. They're not equal. And of course, if there is no f of b, then it would be not continuous either. So if this is an open point, there is no f of b, so you can't even make the argument. Okay. Any questions on that idea? All right, so today we're just kind of going over the basics, like what it means for there to be continuity. It means that you have to have an incoming graph, a point filled, and an outgoing graph, and it all kind of connects into the same spot. If you're at an endpoint, we at least require the point to exist and the graph to touch it, whether it's the left or the right side. Okay, any questions on it? It's not really that complicated. All right, so just for the video's sake, I'm going to put these two are not continuous at A. Okay, now, what about this? Let's draw a picture of a graph. It's going to go from this point to this point, like that. So everybody draw that. So you're going to go from 0, 1 to 1, 0 using a straight segment. 1, 0 is an open point. From 1 to 2, it's going to go closed, straight across, and then open. When you get to x equals 2, y is 2, so there's a bubble right there. Okay, when you're going from 2 to 3, the graph is rising to here. When you're going from 3 to 4, the graph is falling like that. And when you're going from 4 to 5, it's constant. And when you get to 5, there's a point at what looks like maybe 5, 1/2. Okay, so let's just talk about this graph. How would you prove on the AP test, this is a little bit primitive, but how would you prove that the graph is, the function is continuous at x equals 4? Okay, so a test to show that f of x, that's this function up here, is continuous at x equals 4. How would you show that on the AP test? How would you prove it? You got to use limits. Very important. You cannot say, I drew it without lifting my pen. I'm serious. Don't write that. That's too childish. Okay? That's how you can think about it. But it certainly is contiguous here, but you need to write the limits. Okay? You need to say the limit on the left of 4 and the limit on the right of 4 are equal. And they're both equal to f of 4, which is 1. So let's write all that mathematically and it'll give us full credit. Okay? So let's do that. So we would say that the limit as you go approach 4 from the left is 1. And the limit as you approach 4 from the right is 1. And f of 4 is 1. See? And that's how you show it on the AP test. If you write all 3 of those, you're good to go. And then make a little comment about how these are all the same. So you do want to conclude that you got the same answer each time. Okay? If you want to make it a little tidier, you can write this. You can just write the limit as x approaches 4 is this equal to f of 4? This is another way to show your work. And then you would evaluate this limit, and you would evaluate f of 4, and you would say, yes, they're both 1. I personally think this is a little bit better. This shows the left limit, right limit, they're both 1, f of 4 is 1, everything's in agreement. This is a very abbreviated version of that. It may or may not fly. The graders might like it, or they might see it as a little bit shallow. It doesn't have all the details that has. Okay? Okay, now I'd like to prove that f of x is continuous at its left endpoint. So let's go back and look at our graph. Okay, I would like to provide a test to show that f of x is continuous at its left endpoint. So a test to show that f is continuous at its left endpoint is, how would I prove on the AP test that this graph is continuous at its left endpoint? Where is the left endpoint?
0, 0, 1.
Yes, this first point right here. We're talking about this guy. That point right there. Okay. So what was the rule about endpoints?
The limit and the point.
Well, there's no limit there. There's a one-sided limit. The limit on the right matches f of a, right? Okay, so the rule is, since we're at x equals 0, right here, we need to show that the limit on the right side of 0 is equal to f of 0. This is endpoint continuity. It's not really very hard, but what is the limit on the right side of 0? 1. And what is f of 0? 1, correct. So there's not a whole lot of work you can show on an endpoint calculation. You would just put 1 equals 1, basically. Like that. Okay, to be honest, I told you in this class there are 4 styles of problems: graphical, analytical, tables, and also verbal questions. This would more likely show up on the AP test not as a graphical like this one. They wouldn't show you a picture and say prove this and this. They would probably give you a function. Okay, so I'm just letting you know that's what we're going to do tomorrow. So I'll have lots of functions and we'll do continuity tests. Or verbal. Sometimes they'll show you a graph, but the question's very verbal. So it'll say things like, true or false, the graph is continuous at f of 2. Or, the graph is continuous at 2. What do you guys think about that? Look at x equals 2. Think it's continuous? Would you be able to justify why it is not continuous here?
Yeah. The left and right side are 9.
The limit on the left and the right are equal.
But they're not equal.
very verbal. And sometimes there might be more than one right answer, so it's multiple answer kind of thing. A is true, B is true, C is not, or whatever. Like on the SAT with the Roman numeral 1, Roman numeral 2, Roman numeral 3, and you're supposed to pick the first two, or the first and third. You guys know what I'm talking about. Okay, so continuity is a pretty big deal in the test. All right, so what we'll do tomorrow is we'll talk about those, we'll start the lesson off with the warm-up, and then we'll also talk about the points on here that are not continuous, and the reason why they're not continuous. Okay, that's what we'll do tomorrow.